let's go through another example after the one we just did previously with the whole copper and zinc. We'll do one that kind of gives an idea where these numbers come from. So it kind of seems like we just pulled these values out of the back of the book, and what do they really mean? Well, they have to be in comparison to something. So all of those values, whether it's zinc or copper or lead or magnesium, whatever it is, those values are all in comparison to a standard, which happens to be hydrogen. So let's discuss that. Determining potentials using platinum, which is fairly non-reactive, and hydrogen as a comparison. So what this is actually called is a standard hydrogen electrode, also known as, oops, I can spell it, SHE, standard hydrogen electrode. All right, so same scenario we had before, in which you have a beaker, and within that beaker you have an electrode of whatever metal you're talking about, and you have a solution, a 1 molar solution of that metal. And it goes off into the other beaker. And the other beaker, the electrode goes to platinum. And as I mentioned just a second ago, platinum is fairly non-reactive. It's not going to go through the oxidation reduction process. So it's just there. And then you also have some kind of contraption that is putting in hydrogen gas, and it's present. So hydrogen gas is present, available, and it happens to be at 1 atm of pressure, something that matches the atmosphere. And then you also have within this solution a 1 molar hydrogen ion solution. So you have both potentials here for hydrogen. It could be, electrons could be gained and you form hydrogen gas. Bubbles will come out of the solution at the electrode. Or this hydrogen is going to lose electrons, hydrogen gas is going to lose electrons, and that's going to go in and increase the concentration from 1 to something higher, whatever metal this happens to be. And we can measure the voltage over here, and we have a salt bridge, which I won't get into again, but it's a salt bridge which connects the whole system. So just to kind of mark off here, again, what we were doing in the previous video, you have hydrogen which could be losing electrons, and you'll be forming 2 hydrogen ions and some electrons. Or you could have hydrogen ions plus some electrons, and that would form hydrogen gas. Either way can happen based upon the relationship of this metal, whatever it happens to be. Again, magnesium, lead, copper, zinc, a variety of different metals. Based on how these are going to relate to the hydrogen, you could either have a positive or negative value. By definition, hydrogen's value is 0.00. Everything else is in relation to it, and that just defines what these other values are, and that's how we make the comparison, for example, with copper and zinc that we did earlier. Those numbers that we pulled out, that's how they relate to hydrogen, and therefore we can use that as a common comparison. Okay, let's do another example. Wait for the color to straighten itself out here. I just kind of shocked the system. So we'll give this a moment to kind of come back in. There it is. For this one here, we will say we are given, straighten this out a little bit, given some cadmium, and it's 2+, gaining electrons and forming some cadmium. we also have some tin, and that is gaining some electrons and forms tin solid. Now I have the values already present. The values for the cadmium is negative 0.403. Tin's value is negative 0.136, and these are both voltages. So given that information, we are asked to determine which occurs at the cathode and which occurs at the anode. Well, we already kind of talked in a previous lecture that reduction always happens at the cathode and oxidation happens at the anode. But we're seeing probably a little bit stumped here. I might have mentioned it on the side, but we're going to very much spell it out right here. The more positive, or it's another way to say the same thing, is less negative potential, those values we just talked about, occurs at the cathode. So whichever value is less negative or more positive, regardless of the fact they're both negative, whichever one is more positive will be at the cathode. So remember in the previous conversation we were looking at in the equation, I'll pull it up over here again, is you use this equation every single time that it's going to be for the cell cathode minus anode, every single time. So to repeat that process here, if it's cathode minus anode and the more positive happens at the cathode, therefore, for the cell, we're going to say negative 0.136 volts because that's the more positive value up here, minus negative 0.403 is equal to positive 0.267. And again, these are all voltaic cells, which means they're spontaneous. I don't have to force these to work. I just put them in, I connect it, and it just goes. So for a voltaic cell, the more positive value is at the cathode, the negative value is at the anode. And of course, by subtracting it, you get an overall positive value for that. All right, let's move on over to one of our homework problems and give that a whirl. I believe we're on 35. So for number 35, we have pull this down here, a voltaic cell that utilizes the reaction right here. Thallium, chromium, and you get this stuff going on over here on the right. Write the two half reactions that are occurring. Okay, so I just want to isolate these two parts. For the thallium, I have Tl3+, it's aqueous. And it looks like it's going over to still form thallium, but it's just positive. So that's interesting. They're both still aqueous. I went from 3 charge to 1 charge. So in order to do that, I must have added some electrons, negative electrons. So 2 negative electrons went on to that reaction. And for the next one, for the chromium, looks like, oops, not a 3, but a 2. It goes from 2+ over to 3+. And again, these are both aqueous. And for the charge on this one, it looks like you get from here to here, I must have had to add a total or lost 2 electrons. Get from 2 to positive 3. 2 electrons were lost in the process. Okay, those are my 2 half reactions. That's done. But let's just go one step further, just because this may come into play later on. As far as oxidation reduction, this side here gained 2 electrons being added, so therefore that's going to be reduction. And this side here lost 2 electrons. Here they are, they're gone. That's oxidation. By using data from the back of the book, determine the reduction potential for just that one species. So we don't actually have that in the back of the book for this little reaction of gaining 2 electrons. So we have to know information that we have. They told us the answer at the end, the overall cell potential. So I'm going to say positive 1.19 is equal to, again, what happens at the cathode minus what happens at the anode. Well, if I look in the back of the book, I can actually find the value for chromium. I don't have it for thallium. But based on who's doing the reduction and the oxidation, reduction happens at the cathode, don't have its value, but I have this number. When I look this number up in the back of the book, it is negative 0.41. That's its value for chromium, gaining 2 electrons, or electron each. Putting this in, and again, the coefficients do not matter as far as this part goes. So even though there's 2 of them, you only look at it in the one for each element. We don't have to do it for like the stoichiometric value. It's what's called a state function. So it doesn't matter how much, it just equivalates out because it's the charge per, or excuse me, it's the 1 joule per coulomb. So it's proportional. So it doesn't actually affect how many you have because it's proportional either way. Kind of like density. If you have more iron and you ask what's the density difference, it doesn't come into play. It's the same. All right, so when we pull these numbers out, looking at numbers in the back of the book in which we just discovered, minus negative 0.41, we find that our answer will be positive 0.78 volts, which happens to be the value for thallium. That is the answer. Okay, as far as sketching this picture, I'm going to hold off and do that on the next slide because I'm way over time for this one.